All right, guys, this is note card 19. It's called Position, Velocity, and Speed. I'll read a couple of these things and I'll give you some general notes. It says position function, the function s of t or x of t that gives the position relative to the origin of an object as a function of time t. An instantaneous velocity tells how fast something is going at that exact instant and in which direction. Which means how the position is changing with respect to time. And speed tells us how fast an object is going no matter which direction, and measures the rate at which the position changes. So just kind of want to give some general notes here about position, velocity, and speed. So let's say on this axis we have time, and on this one we have position. All right, so we'll call that S of t, and we'll call this t. And we'll measure position in miles, and we'll measure time in hours. So let's say you're going to go on a trip. All right, so when you start your trip, you start at home. So your position from home is right there at the origin, because you're 0 miles away from home. And maybe after 1 hour, you have gone, let's just say, 60 miles. Okay. So let's just, for simplicity, let's assume that you were able to put cruise control in on your car, and it's nice and even. Okay, so assume that's just a line segment. Okay, now maybe over the next hour, maybe you ran into a traffic jam and you were only able to go 20 more miles. Okay. All right. And then maybe you stopped for an hour to eat. So if you're stopped, that means your position's not changing at all. You're still 80 miles away from home. Okay. And maybe when you stop to eat, maybe you realize that you forgot something back at home. So over the next hour, you had to come back home to pick up what you forgot. Okay. So I'm traveling back home, so I'm going back towards the origin. Okay, I'm going back towards my home. So after that hour, I covered 80 miles in that 1 hour, but it's the opposite direction because I'm heading back home. So this axis is miles from home. And let's just stop the example there. Now, what would the velocity graph look like? Let's go over that next. And let me just kind of put the other numbers in here. I put every tick mark to be 20 miles. Well, if you want to think about velocity, what would the units of this means velocity. Okay. Well, velocity is the rate of change of the position. Okay, so this would actually be measured in miles per hour. Okay, but this is still measured in time. So that's still measured in hours. So how do we figure out what the velocity graph is going to look like? Well, what was our rate of change? Okay, what's the slope of this line segment? Well, to me, it looks like I'm going up 60 and right 1. So the slope of this line segment is 60. Let's just do that for each line segment. About for the next one, I'm rising 20, I'm going over 1. So here the slope is positive 20. Here, I'm not rising at all, so I'm rising 0, but I'm running 1. 0 divided by 1 is still 0. So the slope there is 0. And the slope here, I'm going down 80 and over 1. So my slope of this line segment is negative 80. Okay. These slopes of the position function are important. Okay. Okay, so velocity is basically how fast I'm moving. Well, over the first hour, I went 60 miles in 1 hour. So my rate of speed, and it's a nice level increase. Okay, the slope stays the same over this entire period. So between 0 hours and 1 hours, I'm going at a speed of 60 miles per hour. Now, why do I put open circles there? Because this is a hard corner. Okay, that's a hard corner. Over the next hour, between 1 and 2 hours into the trip, I'm only going at a speed of 20 miles per hour. So my velocity is 20 miles per hour. Okay, so that would be that part of the graph. Okay, between 2 and 3 hours, I've stopped to get some food. So my rate of change is 0. I'm not driving in the car. Okay, so between 2 and 3, that would be my line segment. And lastly, between the 3rd and the 4th hour, I'm going back towards home and my slope is negative 80. Okay. So this would be the velocity graph. What's important about velocity? Velocity is the derivative of position. Always. Velocity is the derivative of position. Okay. And whatever the instantaneous, if I drew in a tangent line right here, the tangent line would be 60. If I drew in a tangent line right here, the tangent line would have a slope of 60. Okay, so it's 60 for all the x values between 0 and 1. Okay. If I drew in tangent lines in this little part, the tangent lines always have a slope of 20. So that's why all these values are 20. All these slopes of the tangent line here would be 0 slopes. And if I drew in tangent lines anywhere along that last hour, the slopes of all those tangent lines would all be negative 80. So that's a velocity graph. Okay. Now a speed graph is very, very similar. Okay. Speed graph is very, very similar. The only difference is velocity can go negative. Okay, because velocity is a vector, it tells you a magnitude and direction. So over this last hour, the slope was negative 80, which means I'm going at a rate of speed of 80, but the negative tells me I'm going back towards my home. Okay, so the negative gives me the direction. Speed, let me write it over here, speed is always the absolute value of velocity. Okay, it's just a magnitude. So speed, a speed graph, can never go negative. So it's going to look very, very similar to this graph, to the velocity graph, but this part's negative. Speed can't ever be negative. Just like when you're looking down in your car, it's a speedometer. It tells you about speed. It's not a velocity-ometer. Okay, it just tells you speed. All right, so 1, 2, 3, 4. Okay, so here, this was 60. What's the absolute value of 60? It's still 60. Here, it's 20. The absolute value of 20 is still 20. Here, it's 0. What's the absolute value of 0? It's still 0. Okay, but down here, the velocity is negative 80. What's the absolute value of negative 80? Well, it's positive 80. Okay, so if I was looking down at my car at my speedometer would tell me over the first hour I'm going 60. During the between the first and the second hour, I'm only going 20 miles per hour. During the third hour, okay, my speedometer would tell me 0 because the car is turned off. And then even as I'm going back home, if I look down at my speedometer shows me I'm going 80. Okay, so that's the only difference between the velocity graph and the speed graph. Okay, so here you could also say speed equals the absolute value of the derivative of position. And this S of t means position. Okay. So two ways to write position usually. We usually write position either with an S of t or an X of t. We always write velocity with a V of t. And for speed, we don't have a good letter for speed because we don't want to confuse it with position, so we just write speed. Okay. We just write the word speed. So let's try some of these practice problems. It says, do the following free response problems by hand and then with a calculator. So this is from the 1983 exam. It says a particle moves along the x-axis so that at time t measured in seconds, its position is given by this function. All right, so if I plug in different time values, I can figure out how far the particle is to the right or to the left of the origin. Okay, so it's just like a particle is just moving along an x-axis. Sometimes it goes that way, sometimes it goes that way. So if it's a positive number, it's to the right of the origin. If it's a negative number, it's to the left of the origin. Okay. So part A simply says, what is the velocity of the particle at time 0? And interpret the meaning of the answer you just found. Well, so what they're asking me to do is they're asking me to find V of 0. Well, before I can find V of 0, I have to find V of t. And what do you know about V of t? Velocity is the derivative of position. Well, here they called it x, sorry. Okay. So the velocity function, take the derivative of position, the 3 comes down, so we'd have 3t squared. Negative 6 times 2 is negative 12. Bring the power of t down from 2 to 1. Derivative of 9t is just 9. Derivative of a constant is 0. So here's the velocity function. And to find V of 0, I'm just going to plug in 0 everywhere I see a t. So 3 times 0 squared minus 12 times 0 plus 9, that's just going to give me 9. Now what would the units be? Okay. The position was measured in meters. The time was measured in seconds. So velocity is a rate of change. So its units would be meters per second. And since it's positive, this is a positive 9, that means the particle is traveling to the right. Okay. So we can interpret it this way. At time equals 0 seconds, the particle is traveling at a rate of 9 meters per second to the right. Right is considered positive. That would be the interpretation. Okay, so that's its speed. Its speed is 9, and it's traveling to the right because velocity was positive. All right, part B. It says, during what time intervals is the particle moving to the left? So when a particle is moving to the left, what that means is that its velocity is negative. So we want to find the t values that I could plug in that would end up giving me a negative number for this. So if a particle is moving to the left, we need to figure out where is v of t less than 0. The easiest way to go about this problem is find out where it's 0 first. So let me copy the velocity equation. Okay, let's set it equal to 0. So if the velocity is 0, that means that the particle has stopped. So we want to find those values first. We can do a little bit of factoring. Okay. Pull out a 3, and you get t squared minus 4t plus 3. Okay. Then you could do more factoring. You got a quadratic in there. And you get t minus 1 times t minus 3. That would get me back to this. So using the zero product property, the whole thing's going to be 0 if that's 0 or if that's 0. So you should be able to know that t equals 1 and t equals 3. These are the times where the particle is stopped. So what are you going to do with this information now? Okay, I'm going to make a number line. And I'm going to put these two numbers on the number line in order from of least to greatest. Now, I really don't care what the velocities are. I've solved for times. These are times. At these two numbers, the velocity is 0. Okay. Let's pick a number bigger than 3. Maybe like test 4. So pick a number to the right of 3, like 4. It can be any number to the right of 3. If I plug in 4 to this thing, or you can do it from this version of it. If I put 4 in right there, 4 minus 1 is 3. 4 minus 3 is 1. The number really doesn't matter, but I know that 4 minus 1, that's a positive. 4 minus 3, that's another positive. 3 times a positive would give me a velocity that's positive. What does that mean about my position? Since my velocity is positive, I just put a plus sign for positive, that my position is actually moving to the right there. Because if velocity is positive, it means it's moving to the right. Okay, the particle is moving to the right. Now pick a test value between 1 and 3, like 2 for instance. Now let's plug 2 in to this version. If I plug 2 in here, 2 minus 1 is 1, which is a positive. But if I do 2 minus 3 here, that's negative 1. So that's a negative. So ask yourself, 3 times a positive number times a negative number would wind up being negative, which means that my particle is moving to the left. Okay. Now pick another number. Now let's pick one to the left of 1. Now these are times. Technically you can't have time less than 0. You can pick any number including 0 though. Okay, so let's pick 0. If I put 0 in here, 0 minus 1, that would be a negative number. 0 minus 3, that would be another negative number. 3 times a negative times a negative. 2 negatives together make a positive, times a 3, which is positive, is another positive. So that means between 0 and 1 seconds, the particle is moving to the right. Okay. The question's asking, when is it moving to the left? Here's how we would say it. We'd say the particle is moving to the left over the time interval. Okay, it's this one right here. Over the time interval between 1 and 3 seconds. You can write it as an inequality, or you could have written it with interval notation. Open parentheses. Why are these not brackets? Because at 1, the velocity is 0. So at this exact moment, the particle is stopped. It's not moving anywhere. At this exact moment, the particle is stopped. So we don't want to include the values of 1 and 3, but it's everything in between 1 and 3. So the particle is moving to the left over the time interval between 1 and 3 seconds, and we have to give a reason. Because the velocity is negative. And you can write it like that. And this is enough justification for the reader. Okay. Now let's verify this in our calculator. I'm going to put the position function into y1, but I'm going to use x's instead of t's. X cubed minus 6x squared plus 9x plus 11. Okay, I'm just going to look at, remember my x is like time, so 0 to 10, and then I'm going to do a zoom fit. Okay. Kind of looks like that. And maybe we can mess with it a little bit. Maybe I just want to go negative 10 to 40. Get a little bit better shape of the graph. Okay. So the first question, it says, what's the velocity of the particle at time 0? That's the slope of the tangent line. Here's the position. What's the slope of the tangent line at 0? Second, calculate. Number 6 at time 0. What do you notice right there? It says 9. If I drew in a tangent line right here, it'd be at 9. The slope would be 9. Okay, fair enough. All right. Now, what's happening to the particle here? Well, it's getting, the y values are getting bigger over this first little part. That means the particle's traveling to the right. Okay. Then over this next little part, the y values are getting smaller, which means the particle had to switch directions. So over the first part, it's traveling right because the y values are getting bigger. Then it's traveling to the left, closer back towards the origin, because the y values are getting smaller, and then it goes back to the right. Okay, so if I want to figure out where it starts changing, it goes right, then left, then right. If I use my second trace button, if I look for the maximum here, there we go. It switches at 1. It starts to go left at time 1. If I do the same thing with the minimum, okay, it stops going left toward the left at 3 seconds. So I'm looking for the times. So it's just a way to verify what we did by hand. I think it's actually easier to do it by hand. A few more problems. Okay. It says a dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second. It reaches a height of, gives me some sort of position function here. And it's measured in feet after t seconds. So if I was going to make a graph of the position function, okay, time would go on this axis and height or position goes on this axis. This is measured in feet. This is measured in seconds. Okay. So over time, okay, as time goes on, it's going to get to a high point, and then the rock's going to come back down. Okay. And you should know that this should be a parabola opening down because it's a negative quadratic term. It says do without a calculator first, then use the calculator. So it says find the velocity at 6 seconds. So here they're asking me for v of 6. That's what I'm trying to find. Before I can find v of 6, I need to find v of t. Well, what's v of t? It's the derivative of position. So the derivative of 160t would just be 160, and the derivative of negative 16t squared would be negative 32t. Negative 16 times 2 is negative 32. Make that go down by a power. So therefore, to figure out v of 6, I'm just going to plug in a 6 right there. Uh, 30 times 6 is 180, 2 times 6 is 12, 180 and 12 is 192. So 160 minus 192 is negative 32. Now what would the units be? Okay, the units would be, since it's a rate of change of position, units of position are feet, units of time is seconds. So this would be measured in feet per second. Or if you look at it on the graph, what we're doing here at 6 seconds, what we just found is the slope of the tangent line there. We found the instantaneous velocity. And it says interpret the meaning. At 6 seconds, at exactly 6 seconds, the rock is it going up or going down? Well, it's falling because the velocity is negative. The rock is falling back to Earth at, what's the rate? It's actually 32. At 32 feet per second. Okay, so we took care of the negative by saying it's falling, so we don't write negative again. The actual speed that the rock's moving is at 32 feet per second. All right, if you put a speedometer on that rock, the rock wouldn't know that it's going downward. All it would know is it's going 32. We know it's coming back down because it's negative. All right, part B. It says, what is the velocity of the rock when its position is 256 feet above the ground? And interpret the meaning. And what is the speed of the rock? So there's a few questions to answer. So first thing I have to do, I have to set the position equal to 256. Okay. I have to set the position equal to 256. So what's the position? Position depends on the time. Okay, to me that looks like a quadratic equation. So I need to solve this for t. I'm going to move these two things over to the other side. So I'm going to set that side equal to 0. So I'm going to add 16t squared to both sides. I'm going to subtract 160t from both sides. And then this 256 already on the right is positive. So if I do some factoring here to make the problem simpler, I can take out a 16. So I would divide all these by 16. So I'd have t squared minus 10t plus 256 divided by 16 is 16. And if I keep factoring, that would be t minus 2 times t minus 8. So what that tells me, there's 2 times. At time 2 seconds and at time 8 seconds. At these 2 times, the position is 256 feet. So if I looked at it on a graph, let's draw it. That means, let's say that this was 256, this line was 256. There's 2 times where that happens. At 2 seconds it happens. Okay, but then it also gets to a height of 256 back on its way down. All right, so there's 2 times when the position is 56. What we want to know we want to know the velocity at these two times. So let's figure out v of 2. What's the meaning of that? It's the slope of the tangent line there. And we also want to know v of 8. What's the slope of the tangent line there? So go back to your velocity equation, which you got right here, and plug in 2 and then plug in 8. So 160 minus 32 times 2. Okay, so that's 160 minus 64, or 96 feet per second. If I plug in 8, 160 minus 32 times 8, that's 160 minus, let's see, 3 times 80, or 30 times 8 is 240. 2 times 8 is 16, so that's 256. And that's negative 96 feet per second. So the slope right here is 96. The slope right here is negative 96. Okay. That's not a coincidence. It's because this is symmetric. A parabola is symmetric. And it says interpret the meaning. So I need to interpret these. At 2 seconds, the rock is climbing at a rate of 96 feet per second, climbing because that's positive. At 8 seconds, the rock is falling at a rate of 96 feet per second. So what about the speed? Okay, the speed at 2 seconds is the absolute value of 96 feet per second, which is still 96 feet per second. The speed at 8 seconds is the absolute value of negative 96 feet per second, which is 96 feet per second. So actually at both times, the rock is traveling at the same speed. Just one time it's going on its way up and the other is coming on its way down. Okay. So when it's at 256 feet, the rock's traveling at this rate per second. Now part C. At what point or points, if any, does the position function have a horizontal tangent? What does it mean to be a horizontal tangent? Well, horizontal tangent lines have 0 slope. Okay. So how am I going to figure that out? I'm going to take my velocity function, which is the 160 minus 32t, and I'm going to set it equal to 0 because this has a slope of 0. And it's going to be the high point in the graph. Okay. We want to know what this point is. So I want to know what the x value is there and the y value on the position function. Okay. So I want to know the time, I want to know the t, and I want to know the s of that t. And so if I solve this, just add 32t to both sides, then divide by 32. 160 divided by 32 is simply 5. So the time, notice it's actually symmetric to those two numbers. It's right in the middle. It's 5 seconds. But I also need to figure out how high the rock is there. Okay, so how am I going to do that? I'm going to plug 5 back into the position function. Okay, so now I have to find s of 5. The position function said take 160 times the t value minus 16 times the t value squared. Right. So 160 times, well, let's just leave it like this. This means 160 times 5 minus 16. 5 squared is 25. 160 times 5, 100 times 5 is 500, 60 times 5 is 300, 500 plus 300 is 800. 16 times 25, let's see, for every 4 of those it makes 100, so that's 400. All right, so 800 minus 400 is going to be 400 feet. So this point right here on the graph, the high point, this point right here has coordinates of 5, 400. Okay. So what does it mean to be a horizontal tangent? At 5 seconds, the rock is momentarily stopped. Why is it momentarily stopped? Because its velocity is 0 as a horizontal tangent line. At its high point, or you can use the fancy word of maximum, of 400 feet above the ground. Okay. And part D, it says what's the average velocity? This would mean average rate of change. Okay. So if you go back to your position function, here was your position function. I want to know what the average velocity is over the first 3 seconds. So if this is time 0 and this is time 3, I want to know what the slope of the secant line is. I want to know what the slope of the secant line is. All right, how am I going to do that? Well, all it is change in y over change in x, just over the first 3 seconds. Okay. So what is this point going to be? Well, it's going to be s of 3. Okay. It's going to be the position at time 3. All right, and what is this point going to be? It's going to be s of 0. So my change in y is the difference in these two. So that's s of 3 minus s of 0. And my change in x is this, so simply 3 minus 0. So before I can figure out what this is, I need to figure out what s of 3 is, and I need to figure out what s of 0 is. So I need to plug 3 and 0 back into the position. So 160 times 3 minus 16 times 3 squared. If I simplify, 160 times 3 is 480. 3 squared is 9. 16 times 9 is 144. All right, if I subtract those, let's see, I'm going to get 336, I believe. I did some mental math right, hopefully. And if I do s of 0, 160 times 0 minus 16 times 0 squared, that's just going to come out to 0. Alright, so if I plug these numbers back up into the formula here, 336 minus 0 over 3 minus 0, so that's going to be 336 over 3, which is going to come out to 112. Now what are the units? The units of the y-axis on position are in feet. Okay, so it would be 112 feet per. What are the units of the x-axis? It's seconds. So over the first 3 seconds, the rock is traveling at an average speed, or with an average velocity, of 112 feet per second. Okay. That's the average rate of change. Okay. And you can try to do some of these on your calculator. We're not going to do it for purposes of this note card, but you can go ahead and put it in and see what you get. You can put it in and see what you get. All right. So that's that note card. Now the packet tonight, okay, just try to work your way through it. There's several questions from former free response. But to do part C, if the question asks you about total distance, you have to use this function, which is called an integral. And the way you actually get that, let me show you how to get that on the calculator. All right, to get that symbol on your calculator, you would put, you'd hit math, then you would go down to option 9, which says function integral. And when you do that, you get that weird symbol that looks like an S. And you would just put 0 to 3. Then you got to put an absolute value sign. How do you get absolute value? There's 2 ways. The shortcut, hit alpha and then hit window and choose that first option that says ABS. And then go ahead and type in your velocity function that's given to you at the top of the page. So 3x squared instead of 3t squared minus 2x minus 1. Okay, and at the end you need to put dx. All right, and that will give you the total distance the particle traveled over the first 3 seconds, and just round it to 3 places. So you would say it's 17. So that's how you do that part. All right, try to look at this table and answer some questions. Try to, on the next page, try to understand what type of graphs you're looking at. This is a position graph. This is considered a velocity graph based on what it says in the problem. So just try to interpret what they're asking you for. Okay. Now on several of the next pages, you'll see notes off to the side that says after note card 20. Save these questions until we get done with the next note card. You're not going to be able to answer these until we get done with the next note card. All right. And there's a couple more on the following page. After note card 20, and at the bottom here, after note card 20. Okay, so just give those a shot tonight. But thanks for watching, and I hope the information is starting to make a little bit more sense. Now, some of this stuff, this position, velocity, speed stuff, okay, the big calculus term for all this stuff is, if you see it in any other video, it's called rectilinear motion. So if you see that type of vocabulary, this is the stuff they're talking about. Position, velocity, speed, and even something called acceleration. All that stuff fits under the category rectilinear motion, which is part of the calculus curriculum. All right, so that's it.